The next topic we're going to look at is planning. So today's class, we're going to explain the model of deterministic planning. So we're going to look at what deterministic planning is, and we're going to represent a problem using something called the strips representation for actions. Okay. So far we looked at all these dimensions. The initial one we looked at was state-space search, which is deterministic, fully observable, explicit states, indefinite stages, goals, with perfect rationality. It's flat with a single agent, the knowledge is given, and we're reasoning offline to determine what to do. What we're going to do now is we're going to have a slight change of that. And what we're going to do now is look at planning, and we're going to look at features. So the only one that's changed here is we're going to now look at features instead of just looking at explicit states. We're going to model things in terms of features. Okay, so planning is deciding what to do based on an agent's ability, its goals, and the state of the world. So what the agent can do, what it's trying to do, and it's the state of the world. The initial assumptions are the world is deterministic. In other words, there are no exogenous events outside of the control of the robot that change the state of the world. So we have a deterministic world. The agent knows what state it's in, so that's called fully observable. And we're going to assume that time progresses discretely from one state to the next. And the goals are predicates of states that need to be achieved. So we can have predicates of states that are either true or false we would like to achieve. And what we're going to do is to find a sequence of actions to solve a goal. So we're given a goal and we're given the world, we can observe the world, we're going to find what action should the agent do. So we're going to define an action is a partial function from states to states. So what that means is an action is not always applicable in a state, and an action cannot always be carried out. So that's why it's only a partial function. The preconditions of an action specify when the action can be carried out. We use the term preconditions. We're going to talk about the preconditions of an action. And the effect of an action specify the resulting state as a function of the initial state. So here's an example we're going to look at. So there's a delivery robot that can deliver coffee and can deliver mail. And there are 4 locations. There's a coffee shop, there's Sam's office, there's a mail room, there's a lab. And we describe the state in terms of features. The features are Rob the robot's location, whether Rob, so this has four values in the domain. It's either in the coffee shop, the Sam's office, the mail room, or the lab. Whether Rob has coffee is Boolean, so it has 2 values, true and false. Whether Sam wants coffee is another Boolean feature, so it's true when Sam wants coffee and false otherwise. The mail waiting is a Boolean feature, and Rob has mail, whether the robot has mail is also a Boolean feature. Okay, so there are 5 features, and the actions that the robot can carry out, it can move clockwise around this. It can move counterclockwise, going the other way. It can pick up coffee. It can deliver coffee. It can pick up mail, and it can deliver mail. So they're the actions that the robot can do. Okay. So the first one we might think of doing is to write down an explicit state-space representation. So if you're in the lab and the robot doesn't have coffee and so we're going to use this as before. This means the robot doesn't have coffee, and this means that Sam wants coffee. So if we're in the lab, the robot doesn't have coffee, Sam wants coffee, there's no mail waiting, but Rob has mail, and the agent Rob moves clockwise, then it's in the mail room. So the mail room is the room that was clockwise of the lab. And you should also have robot doesn't have coffee, or Sam still wants coffee, there's still no mail waiting, and the robot still has mail. Okay, so you could think of representing this. You could have a big table of states and actions and the resulting states. That's how we could represent the explicit state-based representation. Okay, but then what happens? You also want to model the battery charge. Well, all of a sudden, all the states completely change. There's now a separate value in the states, and all the actions have to change. So we want what's called elaboration tolerance. As we add different features onto this representation, we want to make sure that we can still represent it. The representation should not change a lot when the requirements change slightly. So if we add an extra predicate, if we also want to model that, then we should be able to add that in and not much changes. So what this idea of elaboration tolerance. Okay, so we're going to look at the main representation we're going to look at. It's called the strips representation, which is the Stanford Research Institute problem solving, which was this is a representation that was sort of one of the very first robots called Shaky. And what they did was they invented this representation for action. So it turns out to be a very useful representation for representing things. And it's simple enough so that we can do things for propositional domains. So the state is a function from, so a state we're going to mean by a function from features into values. So I can represent it as a set of feature value pairs. That's what we're going to do. So a state, for each feature has a value. So it's a function from features into values. And then for each action, we're going to specify a precondition, which is a set of feature value pairs that must be true for the action to be carried out. And we also have the effect is a set of feature value pairs that are made true by the action. So each action we can specify two things, two sets of feature value pairs, a precondition and an effect. And the strips assumption is that every feature that's not mentioned in the effect is unaffected by the action. So all of these features, primitive features are the ones we're going to model here, the ones that aren't made up from other features. Every primitive feature not mentioned in the effect is unaffected by the action. So here's an example of doing that. So here's the action of picking up coffee. Okay, the robot can only pick up coffee if it's at the coffee shop and not holding coffee. So that's what we're going to say. The precondition for picking up coffee is CS, which means it has to be at the coffee shop. So the coffee shop feature is true, and it's not allowed to hold coffee. So RHSC has got to be false. So let's read. So reading this as the robot needs to be at the coffee shop and not holding coffee in order to pick up coffee. Okay, it can't pick up coffee when it's in the office because there's not coffee there. And here we have the assumption that if it's already holding coffee, it can't pick up coffee. Okay, so that's the precondition. It just says you can only do this action, the robot can only do this action when these are true. Okay, and the effect of this is that it just is now holding coffee. After the robot picks up coffee, it's holding coffee and nothing else has changed. Everything else is as it was before. Okay, think of delivering coffee. Well, the obvious precondition is it needs to be holding coffee. So the robot can only deliver coffee if it's holding coffee, and it also has to be at the place where it wants to deliver coffee. And here we're assuming it's at the office. Okay, so the precondition is it has to be at the office and holding coffee in order to deliver coffee. And the effect of delivering coffee is that the robot no longer has coffee and Sam no longer wants coffee. Nothing else has changed. Note that the robot can deliver coffee even if Sam doesn't want coffee. We just know that Sam no longer wants coffee after delivering coffee. So that's how we're going to define the strips representation. I'm going to see a few more examples in class. I'm going to show how it does it in the Python representation for this. Okay, so most of what we're going to talk about in this next part is about deterministic planning. So we're given a description of the effects and preconditions of the actions, given a description of the initial state, and given a goal to achieve. We're going to find a sequence of actions that's possible and result in a state satisfying the goal. We can do this in a number of ways of converting it either into a search problem or into a CSP. All right, thank you all.